All right, so check it out. I was at the play this weekend, and instead of giving me a ticket, like a normal ticket like everybody else had, they gave me this. I was like, it's not even the right date, and I didn't pay that much. And I was like, but I think someone, because no one else, I asked around too, no one else got a ticket like this at all, not even like close. They weren't even the same color, I think. All right, and I was like, this is someone playing a trick on me. They know it's Chase. Like one of my students probably. They printed this up. I was like, that's amazing. So I, as usual, put it on a stark white backdrop and take a photo and put it into this PowerPoint. Did you have a question? Polar functions and complex numbers.
So why did no one else just take it half that?
I don't know. That's amazing, right? Like I said, I think someone was just playing a trick.
Right, so who got admitted?
Um,
Just the name and explain that no one else got this.
okay, too many questions. Okay. All right. Smart one. So we're going to start our last unit today. Pretty exciting, right? It's a little bit lengthy, a little bit. I mean, it's not unusually long maybe, but it's got a bunch of homework so you can see. And it seems like maybe from the title, polar and complex functions, that we're like polar and complex numbers, that we're kind of throwing two things together at the end of the course that like didn't fit somewhere else or something. But that is not at all true. Not even a little bit. Not even a little bit. These are like two beautifully connected ideas. And if you haven't had a chance to think about them, you will soon, and you'll be blown away by the beautiful connection between polar functions and complex numbers. But this is true. The first kind of half, we're going to talk about polar coordinates, get your feet under you when you're thinking about polar coordinates. And just to give you a long view here too, because people wonder, wait, so this is it then? And we're on the last unit. It's only April, whatever this is, 26, 27. 27. So what are we going to do for the rest of the year? The other things we'll do are review type things. I'd like to also have the chance to take an entire IB test. So I'm going to give you that chance as well. There'll be certain problems you can't do. We'll just cross off the ones that have calculus involved and things like that. But a lot of the IB tests you can already do, right? And I just want to emphasize, like when you go someday to take IB tests, make sure that at least some of what you do is you've kept your notes from pre-calculus, and that's what you review in a large part, because the calculus part will be easy for you once you've taken calculus. It's like yawn. The pre-calculus that you'll be like, oh, I forget how to do whatever from pre-calculus. So there'll be a bunch of things we do here. Don't worry, I'll take care of you. Okay, we're not going to be idle. But we are coming to the end of the course, and it's exciting. Yeah.
Wait, so we're not doing the calculus part?
I mean, you can if you want. I'm just saying that's, yeah, whatever you want to do. There will be lots of things you can't do it without.
Just a question, like, how's the IB test formatted? Is it like all like directly right now?
Yeah, it's all. That's why all the tests and things in this class have been structured that way. You know, like your final exam and things like that will be that way too. Again, the multiple choice, just because that's what IB does. I don't think that's wonderful. I pity them for having to grade however many tests they have to grade. Boy, that'd be a huge chore. But yeah, that's how it's formatted. You'll see.
Can we talk about like scheduling, but aren't these places we didn't for a test?
Okay, well we'll talk.
Okay.
We'll talk. For your what? Which one? US.
For ACS history.
Yeah. For US history. Yeah.
Well, I'm not here for 8 weeks.
We'll figure it out.
Hey, I'm not here for the
Like for instance, I test only
No. All right. So my objectives today would be to introduce the polar coordinate system to you, how to name points in polar coordinates, and how to convert between polar and rectangular coordinates and back. Just to introduce you to our new friend, this polar grid. Okay, here it is. This is called the polar coordinate system. And it should actually, even though it's new, kind of, it's not really, right? It's something that you've seen these angle measures before, and this should look maybe not that unfamiliar, actually. It should remind you of like looking at like what someone in a air traffic controller might look at, or like in that your favorite submarine movie, you know, like you're like that's exactly what it should remind you of. This sweeping sonar, you know, yeah, that's absolutely right. Yeah. So then there's a reason for thinking that way. We've also filled in, just for the sake of completeness, really every 15 degrees, every pi over 12 radians I filled in, even though pi over 12 and 5 pi over 12 are not angles you know and love, right? But just to make it complete, otherwise we have this gap in there, okay? Whatever. So there it is. There's what the polar grid looks like. This is called the polar axis. You also know it as the positive x-axis, right? But sometimes we call it the polar axis. And the origin, sometimes we call in polar coordinates the pole, which makes sense. Part of the reason it's called polar coordinates. You can still call the x and the y-axis the x and the y-axis, and you can still call the pole the origin, and no one will complain. Okay, it's not a problem. It's just. And then, of course, how do we name a point in polar coordinates? We name it the following way: r, comma, theta, where r and theta are probably what you would expect. R is the distance you are away from the origin or from the pole, and theta is the angle that you make with the positive x-axis, right? That's the traditional, this should in fact be like, again, this is, Mr. Shakes, this is something I've done before. Yeah, you did. When we were doing vectors, right? This is really just magnitude, comma, direction, right? So really, maybe there's nothing new I'll teach you today, maybe. We're gonna reframe it in new ways, but really it's stuff we've thought about before. So, for example, I put a point on the polar grid there. That's on the third circle out. And imagine that each circle, as we go out, is 1 unit bigger in radius than the previous circle. So how would you name that point? If we're always going to say r and then comma theta, just by convention, there's actually no good reason necessarily to write it in that order. It's just what people have agreed on. Then what would you say? You got it, right? Not a trick question. We could say that's 3, comma, 5 pi over 6. Yes? Now the thing that, already though, maybe this is lurking in your mind, right? The thing that's different about polar coordinates versus rectangular coordinates, which is what you've grown up with, is that polar coordinates are not unique. Like maybe someone else, or like I said, maybe it's already lurking in your mind. Can you think of another equally good way of naming that point? Three comma, what did you say? Yeah, 3 comma 17 pi over 6, is that what it would be? Yeah, absolutely. What else you got, John?
Negative.
Yeah. Oh, okay, yeah. I have these coming up in a different order, but let's just keep shouting them out. So you could say negative 3 comma 11 pi over 6. I like that too. And actually, here, let's get you could also, what would the negative angle be? 5 pi over 6, you could also say, what would this angle be here if you opened it? Negative 7 pi over 6, you could say, is the next one I have up there. But let's make sure everyone's coming with us here, okay? So this is the positive x-axis over here. I'm at the pole right now, and you're going to give me instructions to get to the point of interest, okay? So one way to do it would be the way we initially said, right? Turn 5 pi over 6 units counterclockwise. That's 5 pi over 6 radians. And then walk 3 units. Boom, I'm there. Wonderful, okay. What else could you do? The one we just said is turn 7 pi over 6 radians clockwise and walk 3 units. 1, 2, 3. Again, I'm there. Yay. And then now we should say maybe what Josh said too, and that's that I know this doesn't maybe sit well with us, but are you okay with us letting r also take on negative values? I know that's a little weird maybe, but that's where maybe the departure comes from what we did with vectors, right? With vectors, we thought of magnitude as always being positive. But here, we're going to let r sometimes be negative. It's going to be helpful especially when we're graphing things. You'll see why that's a necessary condition.
When R is negative, how would you, how does that work?
Yeah, so let's physically interpret that. So I think this is what you said, Josh. You said negative 3 comma 11 pi over 6. Isn't that what you said? That would be a good way to do it. So we turn, what does that mean? 11 pi over 6 means I turn 11 pi over 6 radians, based in the positive x-axis direction. I turn 11 pi over 6 radians, and then what does negative 3 mean? Walk backwards 3 units, and lo and behold, here I am again at the same spot. And so those are actually good instructions for getting to that point as well. And then how else could you do it? Could you come up with something negative, comma, something negative? What's another good way of naming the point, but in the way that I just did?
Negative 3, negative 6.
Yeah, so that would be maybe the easier way actually, right? Turn 5 or 6 to the right, clockwise, and then walk 3 units back. Yeah, all of these give good directions to get to the same point. So this is, like I said, a little bit new to us, isn't it? Rectangular coordinates, there is only one set of rectangular coordinates for any given point. But polar coordinates, that's not true. Okay. So how about we do this for this value here? 863, comma 5 pi over 4. Give all possible coordinates. Let's see here. So let's do it in the way that we've just been doing it. Can you name? How about let's ask a simpler question first before we. Can you name even one other coordinate? How about first set of coordinates? Give me another correct name for that set of polar coordinates. Do you have in mind where it is? 863 units in the 5 pi over 4 direction. So we're over here, right? You're welcome to even still say in the third quadrant, right? Yeah. You got a good set of coordinates for us. Another way of saying it, Ashish.
Pi over 4, or negative 863 pi.
Negative 863 pi over 4. I like that. So turn in the first quadrant and then walk backwards into the third quadrant. Okay. Yeah. Andrew. Negative 3 pi over 4. Wonderful. Yeah, and we could come up with some other ones too, right? But it does say name all possible coordinates. So in the same fashion that we might have done when we were doing trig stuff earlier this year, can we name them all? All of them? I mean, one nuance we haven't really said something about is that, like, we could actually, well, actually, Fonda, you hit on this, right? You said, like, you could add 2 pi, right? So, and we could keep doing that, right? Yeah, Mona?
863 pi plus n 8 pi over 4.
Yeah, and you're combining fractions because you're cool. Okay. I wasn't going to even do that, though. I was just going to leave that for the reader. So how about 5 pi over 4 plus, yeah, 2 pi n, and that's, you're right, that's 8 pi n all over 4. Yeah, okay. But that's fine. I'm fine not combining the fractions. But you're right, absolutely, full credit, more power to you. Or negative 863, comma, pi over 4, how about, right? Plus 2 pi n. And I claim that letting n be some integer, positive or negative, that we have actually just named them all, right? And if you think that you have another point that is not on our list, we can prove you otherwise. You know, you might say to yourself, like, so for instance, this guy here is what happens here when n is 0, right? That's not tricky. Or here, this is this guy here when n is 0. This is this guy when n is negative 1, right? And let n be other numbers, and you'll get any other coordinate anyone could ever think of to name this point, right? So that's kind of cool. I don't know that I'll ever ask you to do that again, but it's just, we should, there, we've done it.
Mr. Chase, can you go over again how you got the negative 863
So, yeah, so you can do negative, and then you're subtracting pi from this, right? If you want like a formula, right? So 5 pi over 4, it'll be in the pi unit, 180 degrees off, right? But negative r value, right? All right, so, oops. Oh, it's so disappointing. Need to fix that animation. In fact, I'm going to do it right now, because I can't possibly have you see the answer to this before you actually do it. Don't look. My animation is broken. Don't look. Don't look, Elise. She's looking. Don't make. All right, all better. Okay, so I'd like to think about giving rectangular coordinates now. Finally, I've given you polar coordinates, and I'd like you to give me rectangular coordinates for this. And how would we do that is the question. First thing I might do is draw a picture, right? Here we are, somewhere up here, right? 40 units away, 2 pi over 3 radians. All right, so the question is, what are the coordinates? I mean, what are these lengths? X and Y. This is a problem that you have solved before. Here, give you a little right angle in there if you want it to. This is a problem you've solved before. So figure it out. Ready to go. I know, it's been a while since you did tricks. Don't say it out loud though. That would
Why?
defeat the purpose. Do it in your head. Figure it out. Let everyone struggle with it. Am I right that this is a problem you thought about before in your life? I think so. Yes. So. We figured. Figure it out. What's the question? Yeah. You can call them rectangular or Cartesian. Did you do it? Did everyone do it? What'd you get? Yeah, the answer. Rock and roll. What's the answer? What is it? 20? How about negative 20? And 20 root 3? Okay, wonderful. That is the answer. But I'm curious to hear how people got it here. So obviously if you got it, then you probably are doing it correctly. How are you doing? Describe your methodology. So Steve's excited about it. Go ahead.
I remember thinking about 30, 60, 90.
I mean, absolutely. That is a 30, 60, 90 triangle, the little red triangle I drew. So yeah, anything you know about 30, 60, 90 triangles works great.
I didn't know the rules.
Okay. Anyone else want to throw in a suggestion or comment?
The hypotenuse, which we know is 40, that
Yeah.
is 2x is the thing, and then 30 is x, and then the side adjacent, like across from 30, is x, and the side across from 60 is x root 3. So we know, because we know 2 pi over 3, we know
Yeah,
that
I like
the one,
that.
yeah, we know which side is which, and so x is x, this is the side equivalent to x, and then y is x root 3, so it's just
Yeah, working your geometry mojo on that. I like that. Okay. Okay, cool. Here's another way of, another good way to think about it. Do you have the unit circle memorized?
Yes.
So if that wasn't 40, if it was 1 unit long, what would the coordinates be?
Negative 1/2.
Negative 1/2, comma,
Root 3 over 2.
positive root 3 over 2. Okay. Multiply by 40. Go. Right? Did everyone catch that? Okay, so if we're here, okay. So it's just the unit circle, except not the unit circle. It's 40 times the unit circle. Okay. So that would be any number of ways of thinking through it. I think that the way I just explained it is a good way, maybe just because it generalizes nicely, and we like sines and cosines, don't we? So in general, it's r theta has rectangular coordinates. In rectangular coordinates, we have r cosine theta, r sine theta. We just multiply 40 times the unit circle coordinates, right? Is maybe a good way to say it. I don't know. So up here we have x is equal to r cosine theta, which in this case is 40 times the cosine of 2 pi over 3, which is that. And y, which is r sine theta, 40 times the sine of 2 pi over 3, which equals that. R cosine theta, comma, r sine theta. Going from polar to rectangular is not bad. It's just this. Ready, go. Works every time, you know. So that's cool. Fonda? Yeah, why do we bother doing polar coordinates? Yeah, great question. Maybe this whole unit is a waste, she asks. Yeah. It's true. I mean, right? We should have like existential crises as often as possible, right? Crises? What would you say? Crises? I don't know. Yeah, you're having like a breakdown right now. I understand. I know. Okay. You can just trust me, okay, that they're useful. You'll see. Don't worry. Because you can make pretty flowers. You can't do that in rectangular coordinates. Did you like parametric coordinates? Did you like to remember doing parametric stuff, right? Parametric functions, right? You remember being able to do lots of really amazing stuff in parametric coordinates that you couldn't do with regular rectangular coordinates, right? You could do lots of things with parametric equations. The same will be true in polar, too. You're going to be able to do some cool things in polar that you can't normally do in rectangular. Yeah. What about going backwards? Here's a rectangular set of coordinates. You might need a calculator on this one. Okay, so let's convert this to polar coordinates. And again, maybe a picture is helpful, right? All right, we're down here, -4, 7. You could draw this picture again. This time we have the other information. We're trying to figure out what r is and what is theta. All right, and once we know what r is and what theta are, what r and theta are, then we're done. Okay, so again, figure it out. There you go. I mean, this is reframed in a new light, but not like anything you haven't done. Start with r maybe first. Forget about theta. What's r? How do we figure that out? Geometry students. Yeah, just use the Pythagorean theorem, right? Did everyone get r equals the square root of some stuff? 4 squared plus -7 squared is root 65. 49 plus 16. Doesn't simplify. So there, we're already halfway done. There we have r. Now we just need to find theta. It's a little harder to find theta, but you can figure out how to find theta. I see some people taking other calculators. That's cool. What are you punching into your calculator? I mean, taking a cue from the last stuff we were just looking at, I mean, we could write down that the cosine of theta is equal to -4 over root 65. Excuse me, 4. I wrote this wrong here. What am I doing? And the sine of theta is equal to -7 over root 65. That would be true. But still, I'm wondering, what is theta? People who are having success, what are you typing? I see some people typing stuff into the calculator, so tell me, remind me, maybe rather, what are you doing and how do you find theta? Yeah, right. Yeah, so you could take inverse cosine of 4 root 65, and what'd you get?
1.05.6.
And why is that almost certainly wrong? Because it's positive. So you're okay to do inverse cosine, provided that then you also say negative whatever Simon just said. Right? Okay, so just be careful with inverse cosine, though full permission to use it, as long as you know what you're doing. Okay. Well, because we know it's a fourth quadrant angle, don't you? Yeah, positive 1, I happen to know 1 radian is in the first quadrant. Positive 1 radian, or whatever he said, is in the first quadrant. So it's not going to work. Yeah, Andrew?
So if you subtract that
No, I would just make it negative. You can subtract it from 2 pi if you want. You'll be fine, yeah. But I would just throw a negative sign in front of it and call it a day. What about, do you have anyone have a slightly more efficient way of doing it? Do you remember? We've had this conversation before, haven't we? Sheree, remind us of this conversation.
The inverse of sine.
Yeah. Does that give it to us right immediately? What's that? Is that one a negative 1 point something radians? Negative 1 point, what did you say?
0.51. Well, 0.2.
All right, so negative 1.05 radians. So we could write root 65, comma, negative 1.05 radians, approximately. Those are our approximate polar coordinates for that point. And how else could you do it? You could also do tan inverse. Yeah. What is it? Negative 7 over 4. And you'll get the same thing. So that's a great way to do it too. So just as a reminder for that conversation, you know, okay, we've thought about this before, right? Inverse sine is a good choice because it returns values in the, what are the ranges of these arc functions?
Pi to negative pi and a half for sine.
Sine is from negative to positive pi over 2. It returns values. For cosine, it returns values from 0 to pi. And arc tangent, same as sine, negative to positive pi over 2, right? Just ringing a bell. Remember, if you get an angle, if I give you like negative 4 comma negative 7, and it's in the third quadrant, then like you have to adjust. There's no calculator feature that would get you there. I might do inverse tangent, and then add pi or something, right? Yeah.
I used a system of equations.
Yeah, I used advanced differential geometry to solve this. Anything that gets you the answer is fine with me. Yeah, a system of equations. I mean, that is kind of what we have here a little bit, right? Like, is that what you're saying?
Well,
Or,
yeah.
I'm curious to see what you did. So this, I'm going to star this down at the bottom here, right? With a caveat, right? This is maybe not actually how you're going to find data, though you're welcome to, right? In practice, you can do whatever is convenient. You've had this discussion before, so mature mathematicians of the world, do what you may to find data, please, okay? But certainly, this is definitely the way to find R. Just take the square root of x squared plus y squared. That'll work every time, but you have to be really cautious with the thing I've starred here. That's not like there's no quick and easy way to get data. You really do have to kind of just really think about it. Which quadrant am I in? All that. Eventually what we're doing. I like it. Okay, questions so far? You know how to go from polar to rectangular, rectangular back to polar, you know what the coordinate system is like. I thought just for fun we'd do one last thing, and that's to graph your first polar function, okay? So we can, obviously we want to go here. We want to go in this direction. So in polar coordinates, we haven't said this yet, but theta, we usually treat theta as being the independent variable, and r we treat as being the dependent variable, okay? So let theta range over various things, and then I will tell you what r is based on the theta values you give me, right? So in rectangular coordinates, we kind of go from left to right, right? Dot, 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 and you give me an x value, you plug in, you get a new y value. Here, you give me theta values, and we sweep around, right? And you're going to tell me the distance away you want me to be as we sweep around. That make sense? So starting at 0, and then we're going to sweep around. starting at 0, I'd like you to, and so actually, by the way, sometimes we write this as r of theta to indicate that r is a function of theta, right? Theta independent, r dependent. And by the way, you might like this to be 3 over cosine just because you like cosine better, maybe. Okay. So here's our function. Yeah.
If it's a function, doesn't it have to pass the vertical line test?
No. It just has to have an output for every input, right?
Oh, true. Wait.
Yeah. You're right. If you have a function y of x, if you have a function of x, then it passes the vertical line test in the regular coordinate system, right? But that's not what we have here. We have a function. But it is going to be true. For every theta value, there will only be one r value. So we're good. This is a function. All right, so if you plug in 0, what do you get? 3. You plug in pi over 4, a little nasty, but we can do it. Cosine of pi over 4 is, it'll be root 2 over 2, or 1, right? And then so 6 over root 2, or actually we can do better than that. How about 3 root 2 maybe? Okay, can you get us there? And actually, because I'm going to plot these, so actually let's go down and plot these. 0, comma 3, that'd be here, right? In the 0 direction, we're going out 3 units. 0. So r comma 3, r is 3, theta is 0, 3 comma 0. All right, you'll have to plot the rest on your own, I guess.